We often imagine artificial intelligence as a digital brain, sparking to life through sheer digital magic. The reality is far more mechanical and far more fragile. It is a highly chaotic mathematical balancing act. Modern neural networks contain billions of individual parameters. Left to their own devices, these parameters will not magically organize into intelligence. They will either collapse completely, or they will simply memorize random noise. Taking those billions of chaotic variables and turning them into a functioning model requires building the software equivalent of a hyper-advanced race car. Every component has to be tuned precisely to keep the vehicle on the track. This machine relies on three core pillars. You have the engine, which is the mathematical optimization. You have the safety harness, which is the regularization, keeping the system stable. And you have the high-octane fuel and the track itself, the specialized hardware. These three systems have to operate in perfect harmony. If any single component fails, the entire training process falls apart, and the model learns nothing. This diagram shows the mathematical terrain an AI model has to navigate, known as the loss landscape. Imagine dropping a blindfolded car onto these jagged peaks. Its only goal is to find the absolute lowest point, the deepest valley, which represents the minimum possible error. To find its way down, the model uses a technique called mini-batch stochastic gradient descent. Instead of trying to process the entire dataset at once, it takes small, random samples of data to calculate the slope. This allows the model to feel its way downhill in staggering, stepped movements. But the terrain is hostile. The model can easily slide into a shallow trench, a local minimum, or get stranded on a wide, flat plateau known as a saddle point. Once it stops moving downward, learning halts entirely. To escape these traps, engineers use adaptive optimizers like ADAM, which acts as a dynamic transmission. It tracks the average direction and speed of the gradients, building up mathematical momentum. When the car hits a flat patch, that built-up inertia jolts the model forward, independently adjusting the speed for every single parameter to keep it moving. This chart compares two types of valleys in our landscape, a narrow, sharp ravine and a wide, broad basin. If a model falls into a sharp ravine, a tiny change in new data will push it up a steep cliff of high error. The erratic, noisy path created by our small data batches actually prevents the car from falling into those narrow traps. It literally bounces out of them, eventually settling only in the wide, flat minimizers that can handle variation in the real world. Raw speed alone will not solve the problem. The engine must deliberately navigate through chaos to find a stable, robust solution that survives contact with unseen data. With billions of parameters, these models have immense capacity. If left unchecked, they will literally memorize the training data. Instead of learning general concepts, they create a massive lookup table, failing completely when they encounter something new. This failure state is known as overfitting. As the engine revs and parameters rapidly update, the internal layers of the network begin to shake and shift. The outputs of one layer become the inputs for the next, meaning every part of the model is trying to learn on constantly shifting ground. This diagram shows the model's internal layers. Notice how chaotic those nodes are. To fix this, engineers insert a safety harness called batch normalization. For every mini batch of data, it calculates the mean and variance and rescales the data, locking those wildly vibrating nodes into a stable, predictable rhythm. Then we introduce explicit failsafes, like Dropout. During training, the system randomly turns off a percentage of its own neurons. It seems completely counterintuitive, but by disabling random cylinders in the engine, the remaining parts are forced to pick up the slack. They can never rely on any single neuron, so they build robust, redundant pathways. We also apply techniques like mixup, which mathematically blends distinct training examples and their labels together. This smooths out the sharp transitions in the data, forcing the car to learn broader, continuous rules rather than memorizing exact coordinates. Without these techniques, the network would vibrate apart under its own horsepower. Regularization ensures that the intelligence generated in the lab actually functions out in the wild. We still have to deal with the physical reality of doing the math. A traditional CPU is incredibly smart, like a single brilliant professor executing complex logic perfectly. But when faced with millions of simultaneous calculations for deep learning, the professor is slow. This requires graphics processing units, or GPUs. If a CPU is one professor, a GPU is an army of thousands of simple worker bees. They are perfectly architected to chew through massive grids of parallel matrix math all at exactly the same time. But you cannot simply drop an army of processors onto an unpaved track. Software engineers build hyper-optimized libraries to orchestrate the calculations, ensuring the physical hardware runs at its absolute thermal and mathematical limits. We then multiply that power through distributed training. Instead of one GPU processing the data, clusters of dozens or hundreds operate simultaneously. They instantly share their gradient calculations over high-speed networks, cutting training time from months down to hours. They even cut corners safely using mixed precision training. The system calculates most of the math using smaller, faster 16-bit numbers for speed on the straightaways, while keeping a highly precise 32-bit master copy safe in memory, so the model never loses its exact coordinates. All the elegant optimization math and clever regularization in the world remain completely theoretical without this specialized hardware. This is the track and the high-octane fuel that makes modern AI possible at all. The leaps we see in artificial intelligence today did not stem from a magical algorithm. Engineers built them through the deliberate, painstaking orchestration of these three physical and mathematical pillars. A fast optimization engine without a regularization harness will crash. A harness without GPU fuel goes nowhere. They only function when operating in complete unison. As engineers scale these models from billions to trillions of parameters, the math becomes heavier. The loss landscape mountains grow steeper, and the horsepower required to train them expands exponentially. Yet no matter how massive or capable these systems become, their success will rely on the exact same principles. This delicate triad of optimization, regularization, and hardware will remain the foundational engine driving the future of machine learning.